Greetings, everybody. This is Dr. Gomez. This video will hopefully explain, these are the Chapter 10 Lecture Notes, Part 1. And now we're dealing with what's called the rotational kinematics of a rotating rigid object. Now, what we mean by a rotating rigid object is that it rotates about a fixed axis. In other words, consider this disk here. It could be, a CD in a CD player. Well, it rotates about an axis passing through the point O. The point O is right at the very center of this CD. That point, that rotation axis, never changes. We're not suddenly going to move it so it's rotating about, any other axis. So that's what we mean when we talk about a rotating rigid object. The rotation axis is fixed. So in this case, the disk is rotating about an axis through O. Well, we need to understand the following terms. Remember now we want to get out of linear motion and think, hold on, my cat's walking on my keyboard. Come on, Henry, come here, buddy. So now instead of thinking about linear kinematics like we did back for exam 1, chapter 2, we want to think rotational kinematics. So we need to understand the following rotational or angular quantities: theta, omega, and alpha. And when I say rotational, angular, they mean the same thing. Well, so let's look at a point on this disk called a point P. Well, first let's choose, we have a reference line, typically the positive x-axis. So the point P, its initial position, P, is on the reference line. As the disk begins to rotate, and in this case that gray arrow indicates the direction of rotation, so it's rotating counterclockwise. Well, as the disk rotates, the point P will move through an arc length S. The point P will move from the gray to right there. So it moves through an arc length S, and it subtends an angle of theta, and the point P is at a distance of r from the rotation axis. R does not necessarily have to be the radius of the rotating object. It doesn't have to be the radius of the disk. R is simply the distance from a point on the disk to the rotation axis. So it's the distance from P to O. Well, dust off the old high school geometry notes. Well, what is the arc length? Well, S is equal to R times theta. Or equivalent, or solve for theta. Theta is equal to S over R. Well, theta is called the angular position of the particle, also known as the angular displacement. Typically, it's measured in degrees. In other words, in a certain time t, it starts at t equal to 0, right here at the reference line. Then after a certain amount of time t, the disk begins to rotate. After a certain amount of time t, the point P has subtended an arc length S. It has moved through an arc length of S, subtends an angle of theta, and it's at a distance of r from the rotation axis. And that theta is the angular distance, the angular position of the particle, called the angular displacement, theta, the angle. Well, typically it's measured in degrees, but it's important to be able to convert back and forth from degrees to radians, because when we get to something called the rotational kinematic equations, when you use them to calculate things, the angular quantities need to be in radians. Well, the conversion I use is 360 degrees is equal to 2 pi radians, because I like to think of it as one circle. One complete circle is 2 pi radians. 2 pi, another circle, 2 pi, 2 pi, 2 pi, and we know one complete circle is 360 degrees. So 360 degrees equals 2 pi radians. And 360 degrees is equivalent to one complete revolution. When something undergoes one complete revolution, that's 360 degrees, that's 2 pi radians. Well, what is the advantage of radians? You'd be surprised how many students don't know the answer to this question. Well, a radian is actually a unitless quantity. You know, a radian has no units. It's a way that allows us to do calculations because degrees are not unitless. So for example, if you wanted to do 11 plus 30 degrees, you can't do that. You can't add a real number to a degree measurement. So if you wanted to add 11, the real number 11 plus 30 degrees, that's impossible. You can't do it. But if you convert 30 degrees to radians, you'll get pi over 6. And you can do, and now remember, radian is simply a real number. It's a way of expressing a degree as a real number. And 11 plus pi over 6 gives you 11.52. So now let's look at this figure here. And so we have a point on some rotating object. It could be a disc. It could be one of those little rotating merry-go-rounds in playgrounds. It could be an old-fashioned record on a turntable. It doesn't matter. But it's a rotating rigid object, meaning it's rotating about a fixed axis, the axis through O here. So a point on this rotating object, it will go from position A to position B. It's at position A at some t initial. It's at B at some t final. So relative to the reference line, remember the reference line is the positive x-axis. Relative to the reference line, the point, whatever this point is, we can call it the point P, it has a theta initial, and then that's when it's at point A. And when it's at point B, its angular position is now theta final. So again, it's rotating. It starts at A at t initial, ends up at B at t final. Its angular position at A is theta initial, theta I. Its angular position at B is theta f, and the point is a distance r from the rotation axis. Well, so we know that delta theta is theta final minus theta initial. Well, delta t is t final minus t initial. But typically, like we did with the one-dimensional linear kinematic equations, our delta t, we can just call it t. We'll assume that t initial 0, and then so we just have a t final. So just drop the subscript. So delta t is just t. Well, we wanted to find what's called the angular velocity of the particle, indicated by the Greek letter, the lowercase omega, indicated in the figure here. Again, this is rotating counterclockwise. Well, just like v, linear speed v is change in distance over time, omega is change in theta over change in time. Omega is delta theta over delta t. Well, what is delta theta? Theta f minus theta I. And delta t is just t. So omega is theta f minus theta I all over t. And it's measured in radians per second. Remember, a radian is a way of expressing a degree as a real number. Well, now what about the angular acceleration of this rotating rigid object? Well, just like in linear, a is delta v over delta t, alpha is delta omega over delta t, which is omega f minus omega I all over t. So alpha is the angular acceleration, and it's omega f minus omega I all over t, and it's in units of a radian per second squared. No, come on, stop, Henry, Jesus. Okay, so we have omega, which is the angular velocity, the angular speed. Omega is theta f minus theta I over t. Units of omega, a radian per second. Alpha, the angular acceleration, is omega f minus omega I over t. Units of alpha are rad per second squared. Now, just like the 1D kinematic equations where we only dealt with problems where a is constant, we're only going to deal with problems where alpha is constant. Now, remember from chapter 2, we have the one-dimensional kinematic equations. And here they are. Well, And remember, it's understood that it's for constant A. Well, similarly, we can get the one-dimensional, or not one-dimensional, excuse me, we can get the rotational kinematic equations for constant alpha. And all we need to do is we need to just take the 1D kinematic equations, and we don't need to, we don't want to reinvent the wheel. We want things to be as simple as possible. Just make the following substitution. Just replace x with theta, v with omega, and a with alpha. So just take these four equations, and wherever you see an x, replace with alpha. Wherever you see a v, replace it with omega. Wherever you see an a, replace it with alpha. And you get what are called the rotational kinematic equations. And remember, it's for constant alpha. And here they are in the blue. And again, I just took the 1D kinematic equations and just replaced x with theta, v with omega, and a with alpha. And here they are. And again, it's understood just from top to bottom. This is equation. That's equation 1, 2, 3, and 4. And similar to torque, we define a counterclockwise rotation is positive, clockwise rotations are negative. And so again, we have theta f equals theta I plus omega it plus 1/2 alpha t squared. Omega f is equal to omega I plus alpha t. Omega f squared equals omega initial squared plus 2a parentheses theta f minus theta I. Theta f is equal to theta I plus 1/2 omega I plus omega f parentheses times t. And again, you just take the 1D kinematic equations, replace x with theta, v with omega, a with alpha. And every point on a rigid rotating object, it will have the same omega and the same alpha. In other words, in panel B here on this rotating disk, the point P and this blue dot here, those 2 points, as this thing is rotating, they will each have the same angular velocity omega, and it will each have the same angular acceleration alpha. Alpha and omega obviously are not going to be equal, but in other words, P, this black point P and this blue dot here, even though they're at different distances from O, they will each have the same omega and they will each have the same alpha. And we have the rotational kinematic equations 1 through 4. And similarly to what we did with the kinematic equations, look at what you're given in the problem. You only have 4 equations to work with. You have a 1 in 4 chance of starting it correctly. So let's look. Let me check the time here. All right. Let's look at an example. And it's a rotating wheel. And remember again the rotational kinematic equations. These guys right here. Remember, it's constant alpha. If alpha is not constant, we don't use that. But again, we're not going to, just like chapter 2 with the kinematic equations, we're not going to consider problems where alpha is not constant. And again, equations just in order 1, 2, 3, 4. All right, let's go work an example. So we have a rotating wheel, and its angular acceleration, alpha, is 3.50 rads per second squared. Part A, the initial angular speed of the wheel, omega initial, is 2 radians per second when t is 0. Through what angular displacement theta does the wheel rotate in 2 seconds? And we just want to express the answer in radians and degrees. Okay. Then in part B, during that same time interval of 2 seconds, how many revolutions has the wheel turned? And then at t equal to 2 seconds, what is the final angular speed? So we have alpha is 3.50 rads per second squared. When t is equal to 0, omega I, the initial angular speed, is 2 radians per second. I want to know after 2 seconds, when t is equal to 2 seconds, what is theta? Then part B, how many revolutions has it made during that 2 seconds? And then what is after 2 seconds, what is omega final? Okay, well, let's look at, so part A, I want theta. And this is what I know alpha, I know omega initial, and I know T. So if I know those three quantities, alpha, omega I, and T, which equation will give me theta? Well, I can't use equation 2 because I don't know omega final. So that rules out also equation 3, and that rules out equation 4 because I've been given alpha, T, and omega I, omega initial. So I have to use equation 1. And again, for the kinematic equations, for the rotational kinematic equations, most of the time, not always, but most of the time, we can set theta I equal to 0. So let me go ahead and use equation 1 with theta I equal to 0, and I'll call theta f, I'll just call it theta. So I get theta is equal to omega I t plus 1/2 alpha t squared. I know omega I know alpha, and I know t. Plug in the numbers, and I get 11.0 radians. And then it just asks for radians and degrees. Let me go ahead and I'm going to pause this for a second. Well, I'm going to convert radians to degrees, 11 radians. There's 360 degrees for every 2 pi radians. That gives me 630 degrees. Now, part B, I want to know during that 2 seconds, how many revolutions did the wheel make? Well, I just need to convert degrees or radians to revs, and I did both. So 11 radians, there's 1 rev for every 2 pi radians. You get 1.75 revs. Let me do the 630 degrees. 630 degrees, there's 1 rev for every 360 degrees. Remember, 1 revolution is 1 complete circle. So that's 2 pi radians or 360 degrees. You get the same number. And then part C, I want to know omega final. I want to know what is the angular speed at t equal to 2 seconds. Because it started at t equal to 0, rotated for 2 seconds. Omega I was omega I at t equal to 0. And I want to know what is omega f at t equal to 2 seconds. So I want omega f. I know alpha. So I know alpha. I know omega I. And I know t. And I'm looking for omega f. Well, look at rotational kinematic equation 2. Omega f is equal to omega I plus alpha t. Go ahead and use that. So rotational kinematic equation 2. Omega f equals omega I plus alpha t. Omega I was given, alpha was given, t was given, and we get omega f is 9 rads per second. Now, for the second part of this lecture, angular and translational quantities, I'll put that in a separate video because I'll try to keep them manageable. So let me go ahead and stop this video and get it posted.